1,000 requests per second. Normal, then a database dependency gets slow. Your clients retry. 3,000. 8,000. CPU hits 100%, connections pile up, queues fill. Timeouts spread to other services. Within seconds, a minor network hiccup becomes a full production outage. Your retry logic didn't save the system. It helped take the system down. Retries are load. In this video, we replace blind retries with backoff and jitter. But exponential backoff by itself still contains a dangerous synchronization problem. Most retry logic begins with something that looks harmless. Call the service. If it fails, try again. Distributed systems rarely fail one request at a time. Imagine 5,000 application instances calling the same dependency. The dependency becomes unavailable for 2 seconds, and all 5,000 requests fail together. If every client retries immediately, the service doesn't receive 5,000 requests. It receives the original requests, plus the first retries, plus the second retries, plus every timeout and duplicate still waiting in the system. This is retry amplification. The service needs less traffic so it can recover. But your clients generate more traffic precisely when the service is least capable of handling it. Retries are not free recovery attempts. Retries are additional load. Now imagine the service recovers after 2 seconds. Every client notices at approximately the same time. Every retry timer fires at approximately the same time. Thousands of requests hit the recovering service within the same few milliseconds. This is the thundering herd problem. CPU spikes again. Connection pools are exhausted again. The service falls over again. You now have a synchronized failure cycle. The service becomes unhealthy. Requests fail together. Clients retry together. The recovery traffic overwhelms the service. The system isn't recovering from the outage. It is repeatedly recreating the outage. So how do we break the cycle? Jitter adds controlled randomness to each delay. Instead of every client waiting exactly 800 milliseconds, one might wait 120 milliseconds, another 460, another 730. The requests become distributed across time rather than arriving as a single wave. One common strategy is full jitter. Compute the exponential cap, then choose a random delay between 0 and that cap. Another strategy is equal jitter. Take half of the cap and add a random value between 0 and the other half. Full jitter scatters traffic more aggressively, which makes it a strong default when protecting an overloaded dependency. Randomness prevents thousands of independent clients from behaving like one coordinated attacker. Here is another common production failure. The API gateway retries twice. The service mesh retries 3 times. The application retries 3 times. The database SDK retries 4 times. One user request can now produce dozens of downstream attempts. Platform teams need to decide where retries belong. Prefer one layer with enough context to determine whether an operation is safe to repeat. Inspect the defaults in your cloud SDKs, HTTP libraries, queues, ingress controllers, and service meshes. Many already implement backoff and jitter, but their policies may stack with your application-level retries. Exponential backoff with jitter is only one part of a resilient strategy. Combine it with explicit timeouts, circuit breakers, load shedding, concurrency limits, bulkheads, idempotency, retry budgets, dead letter queues, and useful metrics and tracing. Track attempts per request, retry success rate, added latency, retry budget exhaustion, and the downstream status codes triggering retries. If you cannot see your retries, you cannot tell whether they are improving reliability or quietly amplifying an incident. Now I want to hear from you. What is the worst retry storm you have seen in production? Was it caused by an SDK, a service mesh, an application loop, or retries stacked across multiple layers? Share the story in the comments. Your incident might help another engineer avoid the same failure. If this video helped you, subscribe for more practical videos on reliability engineering, distributed systems, and production incident patterns. I'll see you in the next video.